Yes. So this is the long-term effects of contaminants and breakdown materials from marine artificial structures. And I will start by welcoming our first speaker of the session. That's Sarah Gall from the University of Plymouth on Insight Phase 2 Plastics Project, Legacy Subsea Plastics, from the oil and gas industry, environmental risks of decommissioning in situ. Sarah.
Thanks, Chris. Hi, everybody. So, yeah, I'm here to talk to you about some work that we've been doing over the last couple of years as part of the Insight projects. And it's been a collaboration between ourselves at Plymouth, but with some input from Anthony Andrade at North Carolina State University, who's a plastic degradation expert, which has been really valuable. So, first of all, I think everyone is very familiar with the plastics problem, but there are a couple of key things that I wanted to highlight which are of relevance to the work that we've been doing. And the first of those is that any plastic that enters the marine environment and remains in the marine environment will over time reduce in size to become microplastic and nanoplastic. And the key thing that we don't yet have good understanding of is whether it will ever mineralise in subsea environments. And by that we mean it will return to constituent elements and no longer pose risk of harm. So at the moment, as you can see on the graph on the right-hand side here, we're in a scenario where if we continue under business as usual, the amount of plastic in the environment is going to continue to increase because it just accumulates there, and we don't know whether that is ever going to be able to change. So the key focus at the moment is, from a policy perspective, especially with the current negotiations under the Plastics Treaty, is for us to be reducing the amount of plastic that we're putting in the environment. So we're thinking about oil and gas decommissioning against this backdrop of global plastic pollution, this kind of changing political, and as we've heard as well today, changing public views on all these kind of things as well. So we've got some long-term risks to consider. But we know that plastics are fundamental to oil and gas. There's no way we can do without them. We wouldn't want to be suggesting that that would be a good idea. They are fundamental in pipelines and umbilicals, which have been the focus of our work at the moment. And that's for protection and insulation. But the key things that we were asked to focus on was what would actually happen in decommissioning. How do we need to consider plastics in decommissioning decision-making? Can we decommission in situ, or does that lead to increased risks? And we were trying to unpick these really challenging questions throughout our project. So we've focused on the UK continental shelf area, and we have tried to investigate the environmental risk from plastic. It's just subsea pipelines and umbilicals relating to the oil and gas industry that we focused on, but that doesn't mean to say that these conversations aren't relevant to the other industries. Offshore wind, for example, is putting a lot of cables in at the moment. So all these questions around plastics do have wider relevance too. And we also were lucky enough to get some samples from the environment, so we've been able to actually look at generating empirical data from plastics that have been recovered from service life in the marine environment in the North Sea as well, which has been very valuable. So the first thing we wanted to do to start trying to unpick this was to work out how many tonnes of plastic we actually have in the UK continental shelf area. So we used the North Sea Transition Authority data and had some really valuable input from the Insight IEC to help us to translate the database into something that we could actually work out some estimates of how much plastics there are. So we're estimating that there's 220,000 tonnes of plastics in pipelines and umbilicals on the UK continental shelf. The pictures on the slide here are the samples that we got, which is from Brent Field, so that's some flexible flow lines recovered from Brent Fields. But the focus of most of our work has been on the decommissioning side. So if we were to decommission in situ, the pipelines that are most likely to be those that are decommissioned in situ are large rigid pipelines, as shown here. And at the moment, we have about 120,000 tonnes of plastics contained within those. So that's the plastics that most at risk of being left in the marine environment. And that is mainly coal tar epoxy and fusion bonded epoxy that's contained in those. And as you can see in the picture, there is, on the coal tar epoxy pipelines, there's a layer of concrete weight coating, which will obviously have an influence on how and when plastics degrade as well. So thinking about degradation, clearly we've been studying plastics for a long time. We do actually have quite a good understanding of degradation of plastics in general, but unfortunately when we translate that to the subsea environments, we don't actually understand well yet quite how, what kind of timescales we're talking about and quite how degradation works in those environments. We know though for certain that it's going to be slower than at the surface, but it's likely to be affected by things like pressure and temperature, and we don't yet have good enough understanding of quite what that means in terms of timescales in particular to know exactly what's going to happen to this material. But there's been some great work done in Australia, and we've used that here to give us the degradation rates that we've been working with for our estimations. So that's been really helpful. So the samples that we recovered from Brentfield were provided to us, and we've looked at those. These were in the environment for about 22 years or at 140 metre depth, and Brentfield, as I suspect most of you know, is a relatively benign area of seabed, so there wasn't a huge amount of, well, we didn't think there was going to be a huge amount of abrasion and those kind of processes which might accelerate degradation. But we did find evidence of both mechanical and chemical degradation in the samples that we recovered. To look at them, we looked at the outside of the sample. So the picture here is a cross-section that we cut through the pipeline. That's lots of different layers of plastics, but we looked at the top layer. So the top surface was exposed to the environment. The inside surface of that yellow layer was our pristine sample that we used for comparison. We didn't have any better examples of pristine material that were relevant than that. But we could definitely identify differences between those two layers. So we saw a reduction in thickness and hardness, and also some changes in FTIR spectra, which suggest chemical degradation. And the pictures here, where we have exposed versus pipeline protected under concrete mattress, you can see there that where the pipelines have been exposed to the environment, there is a lot more going on, suggesting again that there's more degradation on pipelines that are exposed versus protected with the concrete mattresses. We then moved on to trying to think about what this all means. So this is where we used the work by Oluwai in Australia, and the degradation timescales that they had modelled. So we took a worst and a best case scenario approach for thinking about this. So our worst case scenario assumes that all of those large rigid pipelines that are going to be decommissioned in situ, potentially, have lost their concrete weight coating, and that's about 120,000 tonnes of coal tar epoxy, and it degrades at maximum degradation rate. So that was modelled by Oluwai, and maximum degradation rate is degradation happening in the presence of sand abrasion. If we think about that, then we get approximately 47 trillion microplastics being produced annually, and it would take about 237 years for all the pipelines to degrade into microplastics. If we take the best case scenario, then we're assuming that the concrete weight coating remains intact, so those pipelines will not be involved. The degradation of polymers would not happen on those. It would only happen on the ones that didn't have the concrete weight coating, and that is fusion bonded epoxy that would be coming off them then, and that would release about 0.4 trillion microplastics each year, and it could take up to 850 odd years for the pipeline to fully degrade to microplastics. Clearly, these are two very much extreme scenarios. It's much more likely that what's really going to happen is somewhere in the middle, but it at least gives us an idea of the extremes that we can work with as we get more evidence to finesse this. To think about this in terms of the risk. So the risk that we have from plastics we know, increases the smaller the plastic particles become. One of the key reasons for that is because there aren't that many organisms that could ingest a whole plastic bottle, but once you get down to the micro or even nanoplastic scales, then it's available to a huge range of, or basically all creatures. So there's a lot more risk associated there, but we wanted to think about what this actually means and what happens to these microplastics. Again, this is all based on quite a bit of assumption, and that's because we don't have the data to make this, to tie this down a bit any harder yet. Hopefully we will get this with time. But we wanted to incorporate fate, so thinking about what actually happens to these microplastics. If they're produced from the pipelines, where do they go? We don't have the real knowledge yet in subsea environments about where the plastics go, how far they might move, and clearly that will depend a lot on the environment in question, how many pipelines are there, what the sediment regime is, and all of those kind of things. But we made some assumptions that if we were thinking about them dispersing, let's assume they all disperse within the water column and none of them enter the sediment, versus if they enter the sediment and don't stay in the water column. So we could take that and then we could get predicted environmental concentration from that. It's common in risk assessment to then compare those kind of things to predicted no effect concentration, and that's the threshold below which there's no adverse effects on marine life. And that allowed us to look at if all the microplastic was contained within certain volumes of water or sediment, where would we be at that point where we tipped into that going over our predicted no effect concentration, therefore posing risk to life. So there are various scenarios under which we have exceeded that, and you can see some examples here for after 20 years, so that's within the service life of pipelines, compared to after about 200 years. So there is considerable risk here, assuming this happens, but that's the big thing. We don't know yet quite what it is that will happen, but at least this gives us a starting point to build on. It's also important to set this all into context. So how does this compare to other sources into the marine environment? We know that this is all considerably less plastics than come from mismanaged plastic waste in the environment, but there are some things, if we were to assume a worst case scenario, then the amount of microplastics does exceed the amount of litter that we remove from beaches with the Marine Conservation Society, and also exceeds the amount of microbead emissions into the North Sea before the 2018 ban on plastics in personal care products. So it's not insubstantial. So at the moment, we are suggesting that plastics should be incorporated into decommissioning in a more formal way. They are incorporated at the moment based on the evidence that we have available, but we don't really have enough evidence for them to be rigorously incorporated. So we are suggesting that the process should be more formalised, but there is a clear need for more information for this to help us to improve our estimates and understand more about what's actually happening. So more empirical studies are needed. The other big thing to consider, though, is that the story doesn't stop when you take it out of the sea. So if we were to remove all of this plastic, what do we do with it then? Is it better to put it in landfill than it is to leave it in the environment? And actually what we really need to be doing is designing better for recycling and to be able to remove things and do something better with them. So I think we've still got a long way to go before we'll be at that point. So it's a really tricky process, but hopefully this progresses us on a little bit from where we have been up till now. So thank you very much for listening, and thanks to everyone who's been involved in helping us. It's been great.